infiniSee 6, namely infiniSee Echo. So before we dive into the interface of infiniSee, which will be the major topic of today's webinar, I would like to set a mindset for each one of us. So the first thing is actually my question to you. Which one of both forms here is actually more similar to the circle in the middle? Is it A or is it B? So think about it for a second. Is it really the circle shape that really is kind of like the thing that matches you, or is it actually the color of the circle that's more resonating with you? If we transfer this whole problem to a molecular setting, so above we have diphenhydramine, an antihistaminic drug, and on the left side we see a very similar compound. We have two thiophene substituted for the phenylring systems. Thiophene is a bioisoster of phenylring systems, so therefore I think we can all agree that A is very similar to our initial compound. And on the right side, there is a little bit of more stuff happening. So now we have a fused ring system in front of us. We lose some flexibility here and there. Additionally, the connecting oxygen atom is now a nitrogen linker. So the hydrogen bond interaction pattern has changed. And furthermore, we don't have tertiary amine on the right side, but an amide. Therefore, this one is no longer protonated under physiological pH values. And therefore, I would say it's pretty obvious that A is the right pick if we think about what's more similar to the original compound, whereas B is, yeah, it feels similar, but it's not really vibing here. So this was easy, but let's take it to another level. So now we have more or less a derivative of the initial compound on the left side, and now a fused isochinoline ring system on the right side. So ultimately, things are a little bit different. We still have like the matching vibes of the ring systems on at A, but B also contains similar ring systems. We introduce a lot of hydrogen bond acceptors on the left side, but on the right side, we still have the same hydrogen bond acceptor in the same position. So here you see the struggle starts. What's more similar? What's the one really fitting the theme? This whole procedure will become even more complicated when you think about this example here. So on the left side, we have a kinase inhibitor, which was also highlighted in several prominent postings on LinkedIn and other popular media. Bitlectinib, a very beautiful compound from my perspective, a covalent inhibitor containing a Michael acceptor. So if we would perform now a search within a chemical space or within even a library, we could end up with compounds A, B, and C. My question would be, which of those compounds would you consider to be the most similar one? While you think about it, I'm trying also to share my train of thoughts here. On the right side, we have the same aromatic ring system. There's my pointer. There's my pointer. So this part is shared. Now it becomes a little bit more different. Here we have an amide coupling compared to the primary amine, aromatic amine here. So also here the shape changes quite a lot. The positioning of the methyl group is different. And last but not least, we are losing the covalent functionality in this part, in this area. So all in all, we could argue, is this even like a similar compound? It's like, this is the only common feature basically, and the rest is just a rearrangement. But ultimately, it would surprise you that this compound A has the highest Tanimoto similarity, so the highest molecular fingerprint similarity among those three. So fingerprint-wise, this is actually the right pick. Now, if we go lower and take a look at this compound, well, we still have the covalent warhead on this side. We still have the ring system in this area. All the changes is kind of like the connecting vector in this area. But overall, I would say that the functionalities are in the right position. Now at the bottom line, we can actually, from my perspective, it's more or less the same compound. Since it's a kinase inhibitor, we can all agree that this area here is the hinge binder. So it's more or less the same thing. We have a different atom here connecting the ring systems, but the left side is still the same. So if you think about it, this would be considered the closest neighbor if we just consider the Tanimoto similarity. Yet, it's not all about the Tanimoto similarity by the end of the day. In this area, we have like a very high focus on functional groups, whereas for compound C, we have a similar arrangement of functionalities. So based on the perspective, all of those compounds could be considered to be very similar to the left compound, and to some degree, all of them address different perspectives. It can become even more complicated if you would also consider experimental data or even 3D data. So on the left side, we have ATP, which is kind of like a very prominent molecule, to phrase it um, conveniently. And on the right side, we have a dye, namely reactive blue 2. So what you should know about reactive blue 2, reactive blue 2 is actually a very promiscuous binder to cholinergic receptors. So basically all receptors that also consider ATP as an endogenous ligand are also inhibited by reactive blue 2. If you would take a look at only the fingerprint similarity or just the flavor of the molecule, you would never say that they both are somewhat similar. Yet, it's just all about the functional groups in this area. So we have the phosphate chains that are usually deprotonated. And in the case of reactive blue 2, we have the sulfonic acids that are also deprotonated. So ultimately, in many cases, reported by modeling approaches, that those residues are actually sharing overlaps with a phosphate group here, making reactive blue 2 a promiscuous inhibitor at cholinergic receptors. So again, similarity comes in different forms and shapes. So to summarize my train of thoughts for you, similarity depends on the perspective, and it also depends on the aim of the project. So what you can do, or what you should ask yourself once you start an exploration in regards to searching for compounds that fit the vibe of your molecule, what do you would like to achieve? Would you like to explore the chemical space around the compounds, or would you like to find close analogs? Or would you like maybe to find compounds that contain particular substructure of interest? Very interesting for fragment-based drug discovery. Next, what you can ask yourself, what parts of my molecule are actually important? Like if you have like an A, B, and C moiety, do you really need the moiety B, or is it just a connector? So if you have flexibility, you should also address this in your search. Finally, the question could also be, well, we have a pretty good candidate and would really like to get some hands on compounds with improved additive properties. So this is also something that you could kind of like aim your search into. And last but not least, as you mentioned, you're struggling with IP novelty. So sometimes you are facing a problem where you just need novel structures. Like you would like to have a new drug for a particular target, and there's lots of FDA approvals for this target. So scaffold hopping can actually bring you to novel structures that address the same target, but maybe with improved properties. So what we come up with, since we have different challenges and different aims, we also need different search methods to actually find the things that fit the topic and fit the theme. And this is where our technology comes in. So today I would like to talk about the different methods. One of them is Scaffold Hopper, and the underlying algorithm behind this one is called actually FTrees. What FTrees and Scaffold Hopper do, they search within our ultra-large chemical spaces for compounds sharing the pharmacophore flavor of a molecule. Very interesting for scaffold hopping, for the name. The next algorithm is actually SpaceLight, and it's implemented as the analog hunter mode within infiniSee. This one searches for close analogs of your compound based on tiny photo fingerprint similarity. And last but not least, the largest addition to infiniSee 6 is the Motif Matcher mode, which runs the SpaceMACS algorithm to run substructure searches within the ultra-large combinatorial chemical spaces. If you are struggling with a PowerPoint presentation not seeing, maybe just re-enter, because I haven't received any complaints so far. Please correct me if I'm wrong, because from my perspective, everything seems to be on the right place. So what we can actually achieve with the different search methods is one, the scaffold hopping approach with FTrees. And you see, once you enter a molecule, like this query molecule, you will end up also with different results. One of them based on the FTree similarity, which is a fuzzy pharmacophore matching, which provides you with a lot of different novel structural groups compared to your initial compound. If you just like to explore the structure-activity relationships of a compound, you can use the closed analog counter, and you will see that all of them are, I would say, pretty closely related to your initial compound. And now the next big thing is actually the Motif Matcher. And it can be run in two different types, namely the maximum common substructure search, which can also be used for downsizing your initial compound, and the exact substructure search, which is of high interest for very small fragments to grow them into full-fledged compounds. And without further ado, I would like to dive into infiniSee 6. Minimize. Oops. And there we go. So, I need to adjust myself a little bit. infiniSee 6 was released, let me guess, 3 weeks ago. And the first thing that we see as a change is if you start a new project, you'll be actually asked what you would like to achieve. If you would like to find scaffold hops, the Scaffold Hopper mode will be presented to you. For closed analog search, the analog hunter. And for substructure searches, you will be facing the Motif Matcher icon. If you just like to organize and assess your compound sets, you can dive directly into the analyzer mode. Let's start with like the most simple thing. I'm sorry if it's too boring for some people, but we will accelerate the speed pretty soon. We will start with the analog hunter. And if you'd like to do a search, the easiest thing you can do is actually draw a molecule. So I will now just enter the easy sketcher in the upper left corner and randomly draw a molecule that I would like to see. You can just do everything with hotkeys. Maybe let's do it like this, because I'm in the mood for a morpho rendering system. And then let's introduce some nitrogen in this area and draw an indole. There we go. And once I laid out my molecule, this is what I'm facing. And this will be my template molecule. So the first thing I will do, I need to select a chemical space I would like to search in. We offer at the moment 6 different chemical spaces. I will get into detail in a minute. And I would like to do a search in Galaxy. In every search mode, on the right side, Scaffold Hopper, Analog Hunter, and Motif Matcher, you can also adjust your parameters by clicking on this icon, namely how many compounds you would like to retrieve. In infiniSee, it's possible to go up to 100,000. If you are interested into having more compounds and also doing a sequential run, you can also use our command line applications. So that's very important for computational chemists. Each of those search modes is also available as a command line tool. There you have also a lot of more of parameters that you can adjust, and you can extract up to 1 million compounds with each command line tool. But let's not overdo it. Let's keep it at 100 at the moment. And for the analog hunter, you can also adjust the minimum similarity of compounds you would like to have. So let's pick Galaxy, and by clicking on the start button, you start your search. It was pretty fast, so fast that you even burden to see. So what I did here, I actually screened 12 billion compounds, 12 billion, yeah, 12 billion compounds within, it wasn't even like a second. It was like 50 microseconds. And I got my results back. So this is actually the power of infiniSee. I can search ultra vast chemical spaces containing billions or even trillions of compounds within seconds on any standard hardware. So it's not like I'm running on a server. I just have my laptop in front of me. This is done actually on the fly at the moment. And once you're done, you get your results. And if I adjust the windows here and here, we can also make it a little bit bigger. I am facing with compounds from Galaxy. What happens here? The structures are also highlighted, showing me the tiny motor fingerprint similarity for each section. And here I'm getting an overall similarity for the whole compound. For the CompChems, again, we are using the ECZP4 fingerprint method. This is like the most common one applied in, I would say, largest part of the industry. If you would like to use other fingerprint methods, it's also they are available in the command line tool. So it holds for those as well. And this is what you will get: many compounds for your initial compound. What's really important about infiniSee and the chemical spaces? The chemical spaces we are searching in are our partners' chemical spaces. So we are collaborating with compound providers, compound suppliers, Enamine, Galaxy from Wuxi Lab Network, Green Pharma. So 6 total spaces, and each result, each compound that you find within those spaces is chemically accessible and can be actually purchased from our partners. So this is like the big twist about this one. infiniSee provides you with compounds that can be synthesized first, and second, that can also be ordered from our partners, from our partnered compound suppliers. If you would like to do a next search, you can always press on the play button, select another space, or just edit your molecule a little bit. So what I will do now, I will introduce a nitrogen here and decorate my molecule a little bit more. Let's introduce some fluorines here. Maybe I would like to have some metal groups here. And maybe introduce an amide in this region. There we go. Nitrogen and oxygen. And there we go. New molecule. I'm clicking on the search again, a few seconds, and I'm getting my next batch of results. So this is how you basically operate infiniSee. You throw in molecules and search those chemical spaces. The question popped up if we can also use other sources. So basically, you can use any one molecule format that you like. You can use SDF. You can directly use SMILES strings as well, and then push them in and then search within those chemical spaces. What's also possible, let's assume we would really like to use one of the results as a query. Just right-click on the molecule and then throw it into one of your favorite modes, like again, Analog Hunter, and the picked molecule, the result, will be the query template. And then you can run another search and again, get all of those derivatives of the compound that are commercially available. Next thing I would like to show you is the export of compounds. So let's assume you really, really, really do love your results. You can mark them as favorites. You can also add comments. Please buy this compound. And what you can do then is actually you can export the compounds in any format that you like. So you can also copy them as SMILES and they'll be saved in your intermediate memory, and then just copy paste them to an editor also. You can also export them as SDF, SMILES, Microsoft Excel sheet, or even the CSV format. So all of those options are available for you. And what you should be aware of is actually that a lot of things can be exported alongside. This includes the reagents that were used for the synthesis of this compound. This also includes a lot of parameters that you can calculate, like the molecular weight, the source of the compound, log P, total polar surface area, acceptors, donors, heavy atoms, and so on and so forth. So anything can be calculated and also exported in your desired format. What else? The next question is if you can use your own external databases. So let's assume you would like to have an SD format, like with maybe 5 million molecules. It's doable. So what you would do, needs to do that, you actually need to add your library into infiniSee. For this, you go into System, and then you go into Search. And in Search, you will have the possibility to load chemical spaces or external sources, SD format, and load them into infiniSee and then use them as for your own convenience. I have to warn you, we are using chemical spaces. Chemical spaces are different databases. So they are combinatorial in nature. I will talk about this in a minute. So if you use large SD sets, it will take a little bit longer to screen them. because all our algorithms are actually based on combinatorial approaches, and the full enumerated sets like SD format um, slow down the algorithms, but ultimately it's possible. If you would like to download our spaces, you can always click on this beautiful little icon here, information. And what will happen then, we will actually guide you to our website, namely here. This is pretty fresh, pretty new. And here you also will receive a lot of information about the chemical spaces. I don't want to bore you with our approach about chemical spaces. What you have to know, the chemical spaces consist of building blocks and chemical reaction rules to make or to create the compounds within the chemical space. This page also features all of the chemical spaces, explaining how they were created, and now also featuring traits of the chemical spaces. Like the Empire space, the newest one, contains a lot of drug-like properties, so very drug-like molecules, hard-coded to be not too large, and that contains a lot of decorated scaffolds. The most prominent space will be the wheel space from enamine, and it's also focused on drug-like properties. And what enamine does in a very amazing way is actually the rapid synthesis and delivery of the compounds. And I have to admit, the compounds are very, very affordable. So ultimately, they range from 140 US dollars to 200 something, based on how many building blocks they require to synthesize these compounds. And it's very reasonably priced, and they get the stuff shipped within 4 to 8 weeks. So very fast, very efficient, and also very pure compounds, which also is a main contributor why a lot of people search within the real space. Okay, back to infiniSee. Just so you know, within the settings, you had a lot of things that you can adjust. Furthermore, if you like to work in a darker environment, you can go to appearance and switch to the dark mode, where things become a little bit more flashy and a little bit more highlighted. For the sake of consistency, I will stick with the light version today. Next thing on my list will actually be the analyzer mode. So I have now selected all of my compounds by clicking here, check all, and transfer them to the analyzer mode. Within the analyzer mode, it's actually possible to assess your data set. So you have the possibility to actually create histograms based on molecular weights, based on log p values, total polar surface area, and a lot of more things, number of hydrogens, and so on and so forth. So pretty interesting. Another thing you can do, you can also cluster your molecules based on the reagent they use for the synthesis. So if you would like to know which compounds are actually using this building block, you can click on this cluster, create filter. The filter will be actually created for you right here. And then once you apply the filters, all the compounds using this building block will be presented to you. If you don't like to see it any longer, remove it and apply filter, and you are back on track. The next thing you can do is actually classes compounds based on their Burmese-Merkur scaffolds. And a very interesting thing if you would like to cover a lot of diversity within your chemical set. Also pretty convenient. And one thing is actually the scaffold itself, where every heavy atom is individually attributed. And if you would like to be a little bit more wide, as I call it, you can also classify compounds based on their skeletons alone. So this is completely agnostic of any individuality of heavy atoms. So it doesn't make any difference if it's nitrogen, an oxygen, or a carbon atom. What's also pretty interesting, you can also classify the compounds by vendor. So if you do a lot of searches, you can all throw them all into the analyzer mode, and then also pick check for all compounds coming from one particular vendor. And last but not least, you can also even classify scaffolds by skeleton. So a lot of customizability here. And ultimately, you can also filter for things like drug likeliness, lead-like compounds, and all of those parameters that you're used to, like number of halogen atoms, heavy atoms, ring systems, and so on and so forth. So this is the very baseline for the operation of infiniSee. Now I'd like to go a little bit more into deeper to give you a feeling for the search results of the different methods. For this, I have prepared some already pre-drafted searches. Maybe I'll start with the first one. And the first one is actually an androgen receptor antagonist. And what I did here, I actually searched all of our chemical spaces, the 7, I also included the virtual one, for analogs or for closely related compounds with a scaffold hopper. So what we are getting here, again, I have to adjust the window a little bit, so it's a little bit larger and you can see everything. What you receive in the scaffold hopper is pharmacophore matching. You can obviously see the local similarities highlighted in their respective colors and the total similarity of the compound in this column. And once you click through the compounds, you will receive a lot of ideas on how they are related. So this is the main topic of infiniSee in regards to visualization. We really want you to understand why infiniSee consider those compounds to be similar. And you get like what you asked for. You get the natural group, also this time featuring an fluorine atom in this area. And what's really important in those projects, this is now from the MBiter space, and I now click through the different spaces, you will notice that the results differ. And this is not trivial. Ultimately, you can see here, this compound is now a 5-membered ring. It's downsized, but still infiniSee considers those compounds to be similar. And what you will notice that the compounds are different because every single space uses its own proprietary building blocks, own chemical reaction rules. And therefore, the chemical spaces share a minuscule amount of overlaps. It always makes sense to, if you have a compound of interest and you would like to see what's inside those spaces of relevance to me, always check all spaces one after another to see which space may cater towards your needs. Let's maybe switch to another one. Now we arrived at Explore. You will see here, again, very similar compounds. And what I would like to highlight in this area, Scaffold Hopper infiniSee in general is agnostic of stereochemistry. So we do not care about R and S configurations. We do not care about E and Z configurations. And especially in the case of Scaffold Hopper is agnostic about the positioning of ortho, para, and meta substituents, as well as the positioning of heavy atoms inside the ring system. So ultimately, you will see that in this case, a lot of compounds are actually considered to be similar to my initial compound. Like all of them have similarity equals 1. In this case, it's the identical compound, right? It's the same thing that I've thrown into infiniSee. In this case, the nitrile group is now switched from the para position into the ortho position. Yet infiniSee does not know that, unfortunately, which is a good thing because the fuzziness brings a lot of spice into the whole procedure. Sometimes people don't like it, but for those people, we also have the different methods. Yet this is something you should be aware of. Ortho, para, and meta are not considered in infiniSee, as well as the positioning of heavy atoms inside the ring systems. So 3 compounds, all considered to be identical by infiniSee, by Scaffold Hopper, FTrees algorithm. But again, you should be aware that they are not all the same. Again, here, a slight switch in the positioning. So no surprises here. Freedom Space also offers a lot of compounds. If you'd also like to know where actually a little bit about the companies, you can always go to the vendor cards here, where all of the chemical spaces are listed, and you can click on them and then visit their web pages to get a little bit more of information about the compound vendors. What you will see here now in this case in ChemWire, we don't have any very similar compounds, so now a little bit of spiciness comes to it. In this case, we have the amide that is considered to be similar to the sulfonamide. Arguable, but you get the vibe. And if you go a little bit lower, you will also see that the compounds become way, way more wilder, but still considered to be related to your initial compound. If you would like to run more than 100,000 compounds with the Scaffold Hopper, you can also use the command line tool. So every time you have infiniSee and have access to one of those search methods, they are also valid for the command line application. So it's not like decoupled. The next thing I would like to do is to show you a little bit more. So I will now load another project. This time I would like to talk about a fatty acid synthase inhibitor. So now I would like to go a little bit more into detail about what is considered to be fuzzy pharmacophorish. So in this case, we can see that the matching of the compounds, and try to enlarge it a little bit more here. We can see that in this case, we have the pyridine ring system here that is matched under the one ring system. Ultimately, it's not wrong. I mean, you have the hydrogen bond acceptor in the ring system, and in this case, it's the same thing. From my perspective, if you would consider the piperidine ring here to the piperidine ring, both match the same vibe. Maybe let's browse to a little bit non so obvious matches. Like here, a tyrosine ring system, and you can see these are always the best scoring compounds. So all spaces provide you with different results. Here we now are matching the how's it called? It's the aziridine ring system. Here at cyclopropane to match the vibe of this ring here. In this case, we are also pretty close. And in the case of Kemwire, we are now also matching the nitrogen here. So it always makes sense to browse through a lot of those spaces just to find something that really matches your core idea. So for the next thing, I would like to talk about the parameters of infiniSee, of the Scaffold Hopper. So let's go with example number 5 on my list. So what we do have here. So I did a search in Explore, and what you will see here is actually that a lot of compounds are related to this kinase inhibitor. If you now scroll down, you will see that even if I reach the 100, all of them are considered to have a similarity of 1.0. So everything is the same for infiniSee, mainly because it's just about the orientation or the positioning of the matches within the ring systems. So as I mentioned here, infiniSee is agnostic of the positioning of heavy atoms. Here, the oxygen is allowed to walk around in this ring system, but is still considered to be a one of similarity. So what you will be facing if you would now go through every single one of them, you will end up with position number 35 to be the exact same molecule. And this is a little bit of a, I would say, not a problem, but this is what you would actually like to do. You would like to have similar compounds, the most related compounds. And to do so, you will end up with a lot of very similar compounds. People ask me, well, is there some way to actually increase the diversity of the compounds? And there is. If you were to take this compound and, sorry, go back. If you take this compound and throw it into the Scaffold Hopper, you can actually adjust the total diversity here. What happens then if you lower the total diversity? infiniSee will start to compare results to previous results. And if they are too similar, they will be thrown off. So basically, compounds that are too similar to your already existing results within the list will not be considered as a result, and it will keep on searching until it finds something that is dissimilar, but is still considered similar to your original compound. So I prepared some searches for you. So as we now look at this, 100 compounds, all of them have a similarity of 1.0 because the connecting of those segments is not considered or not addressed by Scaffold Hopper. But if we now increase or decrease the total diversity, depending on how you look at it, in this case, I decrease it to 0.99. you will now see that my new retrieved compounds are actually not so similar to the previous compound. So with this, I have now extracted a lot more scaffolds that are still very similar to my initial compound. And by doing so, I've reduced or increased the total diversity up to 37 compounds. If I do now the same with 0.98, I end up with only 17 results, but all of them will be very dissimilar to the previous entry in the list. So this is actually a pretty interesting feature to do within infiniSee if you're looking for novel scaffolds. So this was about the scaffold hopper. Let me take a look if there is something I should address in the chat section. So the question is about the matching here. Sometimes it's a little bit disoriented. We are now working on that. The problem is not so trivial, unfortunately, but in nearest future, we will actually also align the 2D representation a little bit better. So now to the Motif Matcher. The Motif Matcher is the latest addition to infiniSee and one of my favorite modes, to be fair. For this, I will now copy a smile string of an SYK kinase inhibitor. It's the same one we used before. And what I will do now, I will actually start a Motif Matcher search. Maybe I will reduce it a little bit. So I will erase this section and just keep the hinge binding motif, something like this. And I will select a space. Let's go with Galaxy because it's the fastest one. And what I can do now, I can actually do two search methods. One is an exact substructure search, and the other one is a maximum common substructure search. I will run now two searches, so you'll see the differences. When I run an exact substructure search, I'm requesting only compounds that feature this particular structure of interest within them. This will now take some seconds. Unfortunately, Galaxy was not able to find something, so this particular compound is not featured within Galaxy. Yet, if I do now a maximum common substructure search, I will see a little bit more. And there we go. So what happens here? I get, again, a lot of results, and I get a coverage. So how many percent of my initial compound are actually present in my result molecule, as well as the maximum common substructure size. And if I now both the results, I see what's available. And what's the beauty of this approach? Since I'm not doing an exact substructure search, I'm also receiving compounds that are maybe not overlapping in one particular heavy atom. So again, here you get a beautiful visualization of highlighting of the most important results. What you will also notice, and I think this is actually something that is not addressed enough by us, is the fact that a lot of those compounds that can be synthesized are building blocks themselves. So sometimes you are facing a particular problem where you need a lot of building blocks just to decorate your scaffold, to explore structure-activity relationships, or improve attribute properties. A lot of compounds that you can extract from our chemical spaces are beautiful building blocks themselves. For like those kind of things, we also receive a lot of them with bromide. You can do a lot of Suzuki coupling with them. So it really makes sense also to use smaller compounds within the Motif Matcher to actually check for potential building blocks that you can easily purchase and don't need to synthesize, because building block synthesis is a really tough challenge sometimes. Again, if you feel like, oh, I really like this compound, you can click on it and just reuse it for another search. So I'll just use one of my result compounds, put it again in the Motif Matcher, and then do an exact substructure search to check for any compounds that are present here. So not working. I will just run another maximum common substructure search, and there we go. A lot of compounds, and they are all synthetically accessible and can be purchased. So this is how you would run an MCS search. So now I would like to give you a little bit more of perspective on how to abuse this method. One method is actually for fragment-based drug discovery, and for this I have example number 4. Riclecitinib. So this time I have removed the meta group here just for demonstration purposes, but don't lose a lot of information here. So what I receive here, I receive actually the finalized compound, and I receive quite a lot of derivatives that contain the substructure. All of them, or several of them, also contain modifications in the Michael acceptor, so you could use also fine-tune the reactivity of the group. And this is like the large, this is huge for fragment-based drug discovery, because you can mine for all compounds containing your fragment binder from the chemical spaces, and then just work with them. Do a docking afterwards, and then purchase the compounds that you like, or apply any other methods to actually look for them. Again, just to kind of like browse through the different results, this was not covered by real space, surprisingly, for me at least, but it's present in the explore space. A lot of derivatives are also present in the freedom space, not in ChemWire though, but a lot of them are present in Galaxy as well. So it always makes sense to screen all chemical spaces to get an idea of what is actually synthesizable and is also commercially available. It's also pretty nice if you do a larger search. So let me load the same search, but with 100,000 results. And this is like huge. I used this particular substructure, did an exact substructure search. So all my compounds coming from the explore space contain this molecule. And I was able to extract 100,000 compounds. And I'm not even at the top. If I would use the command line, I go even higher. And what you will see here, the compounds become pretty large. I don't know if I can zoom in enough. So you will get a lot of chemical diversity here. So for fragment growing, this is huge. And if you just go through the list, you will also notice that all of them are actually quite diverse, contain a lot of modifications, and all of them can be ordered and synthesized. And it's just mind-blowing how much you can actually abuse this approach for substructure searches. What you can also do subsequently to go to the analyzer. From my perspective, I preloaded them already here, just to get a feeling for the distribution of the compounds. And you will see here that even without applying too many constraints, I'm still pretty close to the drug-like rule of 5 range of the distribution. And if I would like just to downsize my compounds, that's what I can do. I can just click on this particular region, create filter, and then filter my compounds only for this region. And then I'm presented only with smaller derivatives. The struggle I have personally sometimes, this is just the nature of the approach, that a lot of halogens are included. So I tend to actually remove them. Where is it? Halogens, and I would like to have 0 and apply filter. And then even like for this minor section, I'm ending up with 7,000 of compounds, and all of them are containing my substructure of interest. So you see, it is quite a powerful method and quite a powerful tool. The question is if there are any 3D similarity functions within infiniSee. Nope, there are not as of now. It's a purely 2D based method, so a 2D platform for ligand-based drug discovery. I always recommend, if you have anything available, like a X-ray crystal structure or other 3D methods, just use infiniSee to mine for those compounds, and then you need an additional enrichment. What I also like to do, I like to combine different methods. So I like to use FTrees for collecting a lot of compounds with novel scaffolds. And then I use this particular sub-library, and then I run an additional additional screening with the same query compounds on my FTrees results to see if anything really matches. Because if I have a high FTrees similarity and low tiny motor similarity, then I'm in the section where compounds become interesting, because this is where the real scaffold hopping happens. Okay, so I think I've convinced you about the power of the Motif Matcher. Another thing you can do with a Motif Matcher, maybe let's go with example number 7. No, I don't need it. I just can go to the Motif Matcher itself. Motif Matcher, I will now throw in another smile string. So this is now the compound I'll be using. And I will run an exact substructure search within Galaxy. Again, screening billions within seconds. And I received 92 compounds that actually contain my substructure. And if I now just kind of go a little bit lower, you can actually also see how those compounds grow. What's also pretty interesting, this is how you can also kind of like combine or guide the search. If you see that a particular structure is actually present within your chemical space, you can just use this structure to run new searches. So this by doing so, you can actually expand your compound one by one to grow into the drug-like area if you start with a fragment. Another thing I would like to mention is actually that you can apply constraints within the Motif Matcher. So let's assume we would like to know, are there any compounds that actually contain this substructure? So you apply your constraints on this area and then run an exact substructure search and receive only those compounds containing your highlighted motif of interest. The rest of the molecule will be ignored. And you see all of my compounds contain now this section. What's also possible is to apply searches if you highlight something with a maximum common substructure. So again, once I have applied my constraints, the rest of the molecule will be ignored, and I can run a maximum common substructure search. And there you go. Compounds will be a little bit more diverse when I go down, because also the ring system will change a little bit. So you see, also quite handy if you have a very large compound and would like to put an emphasis on one particular feature. I think that's basically it from the operation side. What I would like to mention is actually the limits of particular things. So don't expect too much from natural light compounds. This is very important for me personally to address this. The chemical spaces that we are using right now are agnostic of stereochemistry, and therefore they use building blocks and very robust chemical reactions. Robust chemical reaction is not made from natural compounds. So if you would run something like morphine, it is a very natural-like compound. And then maybe not here, let's do the analog hunter search. So let's see what would be the closest compound based on tiny motor fingerprint similarity in Galaxy. And this is my hit. We can argue if this is like a similar compound, yet I'm quite surprised, to be fair, that this looks very similar to papaverine. So ultimately, it's actually not a bad hit. But if you go lower, you will see that it's not really catching the vibe. So natural compounds and infiniSee are not good friends at the moment. Maybe we'll have a natural compound base in the future, natural compound chemical space in the future. But as of now, it's just not the vibe. So be careful, don't expect too much. Maybe what do I have here? I also have something for the an inhibitor of the human herpes virus. Oops. Okay, then let's go with this compound. Pretty wild, I think we can all agree. Let's see what happens if I run a search. And I mean, yes, but no. So don't expect too much if you use natural compounds because the chemical spaces are just not addressing this area right now. Yeah, this is actually what I wanted to show you. And now if you have any questions, feel free to ask. If you would like to run a search with one of your compounds, you can request it right now. But from my perspective, I'm more or less done.